Greetings, class. This is my first video for you guys. It's a work in progress, and I promise you it'll get better as it goes. I'm going to learn and do my best. These are some notes that I had from last year, so they're already written, and I'm just going to go through and explain them to you. I asked you to read the first couple sections on differential equations out of your book. And I said read the whole section if you felt like it. I think it was chapter 4. I said 4.1, 4.2, and 4.3 or something, but if you could do the whole chapter, it would be cool. So the next topic we're going to get into is differential equations. And so we start by defining it. So a differential equation, otherwise known as an ODE, and the O is just for an ordinary differential equation, because there are PDEs, but you have to get to Calc 3 to understand partial derivatives, and so we're just doing ordinary derivatives. But the definition of a differential equation is it's an equation involving y and or x and one or more of the derivatives. And so algebraic equations look like this: 2x plus 1 equals 8. Notice there's not any y's in here, there's no derivatives, nothing like that. X squared plus 5x plus 6 is 0. Again, no y's in there, no derivatives, nothing like that. E to the 2x minus 4 equals 18. No y's in there, no derivatives in there, nothing like that. In an algebraic equation, the solution is always a number. That when you substitute back into the equation makes it true. And so in this one, 7/2 would be the answer. So, and if you subtract 1, you get 7. Divide by 2, you get 7/2. 2 times 7/2 is, the 2's would cancel, so you get 7, and then 7 plus 1 is 8, and so it checks out. But the solution is always a number. That's the important thing. X equals 7/2. X equals -3 and -2. X equals the ln of 18 plus 4 divided by 2. Something like that. Now, differential equations, we said, have y's, x's, and or, and then also some of the derivatives. And so here you have a second derivative and a first derivative and the function. Then you have an e to the x. So you have x's, y's, derivatives. Here you just have a derivative, but then you have sine x, so you have x's and derivatives. And I said and or, so it could be y or x or both. Here, y triple prime plus 2y prime is tan x, so you have something like that. Y double prime plus xy equals e to the tan x. Y prime equals y squared plus 2y plus 1. Notice all of these have x's, y's, either or both, or one, or but at least there's a derivative in all these. Here there's even a fourth derivative and a second derivative and so on and so forth. The difference between a differential equation and an algebraic equation is that a differential equation, the solutions are functions. So this is like, can you find me a function y so that when you take two derivatives of it and then one derivative of it and multiply it by 5, and then you just take the original function and multiply it by 6, and you add all of those together, it comes out to be e to the x. Can you find a function that does that? That's the question. And so, and if you can, then that's the solution. And if not, then it's not a solution. So, for algebraic equations, solutions are numbers. For differential equations, solutions are functions. And so here's a couple examples. So on the 2x plus 1 is 8, we already said check 7/2, and if you check it, you get 8 equals 8, which is true. On this one, the y double prime plus 5y prime plus 6y equals 0, I'm going to have us check that e to the -2x is a solution. Well, look, to do that, I need two derivatives, one derivative, and the function. Well, I have the function. It's e to the -2x. So we take the first derivative. So that should be a derivative of e to the stuff is e to the stuff times the derivative of the stuff. That's why we pop a -2 off. And then the second derivative, we need it also right there. So now the negative 2 stays. The derivative of this is e to the negative 2x times another negative 2. And that negative 2 times the negative 2 gives me a positive 4. So now where the y double prime is, I'm going to put 4e to the negative 2x. So you see right here, it matches where the y double prime is. Then I got plus 5, and then I need y prime. So y prime was the negative 2e to the negative 2x. And then plus 6y, and I gave you the y as the solution. It's e to the negative 2x. But I'm questioning right now, is that going to work and give me 0? Well, on the next page, you get 4 and 6 make 10 minus 10. So you get 0 equals 0. So that shows that this function is a solution to this differential equation, where this number is a solution to this algebraic equation. So solutions to differential equations are functions. Couple important things to know. The order of a differential equation is just the highest derivative that shows up in that equation. And so, back to this. The highest derivative that shows up in here is the second derivative. So I would call this a second order differential equation. This, the highest derivative, is the first derivative. That's a first order differential equation. Here, second derivative, and so that's a second order differential equation. This is a third order differential equation, a fourth order differential equation, and this is a first order differential equation because it's the highest derivative, not the highest power. So I don't care about the 2, I care about what is the largest numbered derivative that shows up in there. So it's kind of like the degree of a polynomial, if you think about it. That's the way I kind of look at it. So that's what the order of a differential equation is. Just the highest derivative that shows up. Now, linear versus nonlinear. So we want to know, is the differential equation linear or not? And so there's a definition in the book that says that a differential equation is linear if it can be written in a certain way. And that is very confusing. So what I say is a differential equation is linear if none of the y's have been tampered with. And I'll show you in a second set of notes what that actually looks like, the linear versus nonlinear part. All right. There is one class of differential equations you already know how to solve, and that's the derivative is a function. So if I told you that the derivative of y with respect to x was f of x, or y prime was f of x, if you wanted to know what y was, well, how do you get from y prime back to y? You integrate. And so if I integrated that side, then I should integrate that side. And so the same thing over here. If you had the derivative of y with respect to x and you integrated it with respect to x, you'd get y. But if you integrate this side with respect to x, you must do the other side. And so the solution is that you get the integral of f of x. If you know the derivative is f of x, then the solution is the antiderivative of f. But you know these come with a plus c. And you know that since 1a, I've hammered you about that plus c. That plus c has to be there. It's non-negotiable. And so what that does is it actually gives you a class of functions. So when you first solve and get that plus c, that's called a general solution. So, for example, if you're going to solve dy dx is 2x, well then if I integrate this side with respect to x, I'll get y. And if I integrate this with respect to x, I'm integrating 2x. And that's x squared plus c. And now, for every choice of c that I get a different parabola. Just shift it up or down. Like x squared plus 6, x squared plus 4, x squared minus 2, x squared minus 7. And those form what we call a family of functions. That's why it's a general solution, because we say in general they look like a parabola. Just shift it up or down. Notice we could check, so we could check that that is a solution. So to check it, the derivative of that should be 2x. So if y prime is 2x plus 0, which is 2x, and so I get 2x equals 2x, so that checks out. So that is the solution to that differential equation. That's the easiest one to solve. When you know the derivative is a function, then what you want is the antiderivative of that function. Now let's say that we're going to solve dy dx equals 2x, and I'm going to add something. I'm going to say subject to that y of 1 equals 5. When I give you this, I'm giving you what's called an initial condition or an initial value. This is a point. It's x is 1, y is 5. So it goes through the point 1, 5. Now, we've already solved this and we know that we get a family of parabolas. But there's only one parabola right here where it goes through 1, 5. It's the one I've darkened in black. And so that's the one that I want to know about. And so I would go through and solve the differential equation. So we get y equals the integral of 2x, x squared plus c. When it has the plus c, that's called the general solution. And then now I'm going to use that x is 1 and y is 5. And so where y is, I put 5. And where x is, I put 1. And then when I subtract the 1 over, I get c is 4. And when I plug that back in, I get y equals x squared plus 4. Now notice, this is a very particular parabola. There is no other parabola that would lay on top of it except that exact one. And so that's how it goes from a general solution with the plus c to a particular solution. But to get there, you need an initial value or an initial condition. For that reason, a differential equation coupled with an initial condition is what we call an initial value problem. So every time you solve a differential equation, you always get a general solution. But if it comes with an initial condition or an initial value, then when you solve it, you will get a particular solution, and that comes from an initial value problem. Okay? So the first way that you learn how to solve a differential equation is a method called separation of variables. And I do it a lot more stringent than the book does. And so I have an example here first of just how it works. And you got to kind of bear with me because it started different, okay? So this differential equation started as dy dx equals y times sine x. And what I've added then is I'm going to separate variables. And what that means is, to separate variables, I want all of the y stuff on one side, and I want all of the x stuff on the other side. So that separates the variables. You have one variable on one side, one variable on the other side. And when I say the variable, I mean all of it, okay? So if I want the y, because I don't want it with the x, so I'm going to divide by y, so that'll cancel. And then I put a 1 over y over here. Now, what they tell you to do, and this is what I spend an entire page trying to show you how you get around, is they say then just multiply both sides by dx. But I've told you since day one that dy dx is not a fraction. It's not something you can break apart. It's not so you can't just multiply both sides by dx. That's why in red it's written that's illegal. That's an illegal move right there. But it works, and so we do it. But I'm going to show you the legal way to make that actually work. Now notice on this side, once the dx's cancel, I have 1 over y and dy. So that's only y stuff on that side. And on this side, I have sine x and dx. So on this side, I only have x stuff. But once you have 1 over y dy and sine x dx, that's perfect to add an integral to both sides. So once we add the integral to both sides, then The antiderivative of 1 over y is ln absolute value y. And the antiderivative of sine x is negative cosine x. Technically, you get a c from this integral, and you get a c from this integral. Since they don't have to be the same c, I call one of them c1 and one of them c2. But I can move c1 to the other side. And c2 minus c1, if c2 is a constant and c1 is a constant, then c2 minus c1 is just another constant. And so I'm going to rename it as a new c. So that's what we do there, is rename it as a new c. But now I want to solve for y. And so to solve for y, I e both sides. The e and the ln cancel. I get the absolute value of y is, and this, once you have e to a sum, you can make it e to the negative cosine times e to the c, because remember, when you have same base to powers and you multiply, you add the powers. So then I've got the absolute value of y is, and if c is a constant, e to the c is also a constant. And so this e to the c is what I renamed c right here. And that's something that's done over and over again in differential equations. Every time you get a c or a 2c, 2c is just another c. C plus 5 is another c. E to the c is a new c, because e to a number is a constant number, and so it is just a constant. And so why not call it the most simple constant, and that's just a straight c. Okay, so that is the process of separation of variables. But how do you actually get there? So here's the deal. A differential equation of the form dy dx equals f of x times g of y is called a separable equation. So it has to be multiplied in there. If it's added, you'll never be able to separate it. And so you must have it multiplied in there. To solve this, we use the method called separation of variables. And I already kind of demonstrated it up here. So here's how it really goes. You start with dy dx equals f of x times g of y. I'm going to divide by g of y. I'm getting y stuff on this side again. But here's the thing. This time I don't multiply by dx. Why? Because I told you it's illegal. And so you can't do that. And so now, just for a little bit of simplicity, I'm going to let p of y be 1 over g of y. Why? Just because I don't want to keep writing a fraction every time. So 1 over g of y is now p of y. Now, we've got p of y dy dx equals f of x. So now I'm going to suppose that I already know the solution. So let me suppose that phi of x is the solution. So this has a solution, and it's phi of x. And so if y is phi of x, then dy dx, the derivative of that, should just be phi prime. And so where I have p of y, now that's p of phi of x, and dy dx, we said was phi prime of x. And so that's where both of these two things come from. The arrows lead over to those, and you see where that's substituted in. So now I've got p of phi of x times phi prime of x equals f of x. Now we're going to integrate both sides with respect to x. And so I've got the integral of p of phi of x times phi prime of x dx equals the integral of f of x dx. This actually takes a u substitution. If I let u be phi of x, then du is phi prime of x dx. And look, phi prime of x dx is right there. So then when I substitute, I have the integral p of phi of x. Well, phi of x is u, so that's p of u, and then du. And then on the other side, since we're integrating both sides with respect to x, I just get the integral of f of x dx. But u is just a dummy variable. And so it doesn't matter. The integral p of u du is the same as the integral p of y dy, is the same as the integral p of z dz. It's the same as the integral of p of smiley face d smiley face. And so, but remember, what was y early on, or P of y. P of y was 1 over G of y. So where this was, I say it right here, but P of y is 1 over G of y, so we get 1 over G of y dy equals the f of x dx, and then we integrate both sides. But if you look, what it looks like we did is we just took and divided both sides by G of y, and then I multiplied both sides by dx, and then I integrated both sides. And so at this point it's separated, and then we integrate both sides. Now the thing that you have to understand is all of this work up here to derive it, all it did was it made me not do this one illegal move. But here's the deal. In the end, because I noticed this, and I said, well, in reality, I could just start with that, divide by G of y both sides, and then even though it's illegal to multiply both sides by dx, the dx did come off the bottom of the dy, and it wound up on the other side. So let's just put it over there. So it is like we multiply it over there, but this is illegal to do. We do it, though, to not have to do this whole page every time we solve a problem. So we do it to make things simple. And that's the reality of what actually happens. So that's how you do separation of variables, okay? Now let's take a couple look at a few examples. So one of the most famous one is the exponential growth. And that starts out as dy dt equals ky. So you can see in blue, that's the original differential equation. dy dt is ky. Now I'm going to separate variables. So I'm going to divide both sides by y. I got 1 over y, and then the dy dt. Then we do the illegal thing that we're not supposed to do, but it works, so we do it. So we multiply both sides by dt, and I get 1 over y dy is k dt. Then I integrate. The antiderivative of 1 over y is ln absolute value y. The antiderivative of k is kt plus c. Just like before, technically it's a c1 and a c2, but if I do that, I can rename c2 minus c1 as a new c. To solve for y, I e both sides. I get the absolute value of y. This breaks apart as e to the kt times e to the c. E to the c is a constant, so I'm just going to make it a new c. And here's the thing. Normally, you can't just drop absolute value because you don't want to deal with it. And so, how do I get around that? Well, here's the thing. If you know the graph of e to the x, it kind of looks like this little line right here. It's never negative. It's asymptotic to 0 at negative infinity, but then it's exponential growth. And so this is always positive, and this is always positive. And so this whole side's already always positive. And so the absolute value then doesn't matter. And so I do not write the absolute value up here, but not because I'm stupid or because I'm careless. I don't write it up there because in this case it truly is not needed. So then I get y equals c e to the kt. And if you remember exponential growth and decay from like Math 20, you remember y equals p naught e to the rt for like interest rates and continuously compound interest. This is where it comes from. It comes from this differential equation. And this differential equation, let's talk about it just for a second. This says the rate of change of a population. So let's say y is some population. So this says the derivative of y with respect to t, let's say t is time. So if y is population and t is time, then this is the change in population over the change in time. And that is a multiple of how much there is, how big the population is, because y was the population. That means that the rate of change of the population is proportional to the size of the population. There are many things in life that follow this. Rabbits, breeding. So the rate at which the population grows in a rabbit population is directly related to how many rabbits there are. If there's only 2 rabbits, you ain't going to have many rabbits once you have a birth cycle. But if you have 2,000 rabbits in that same one birth cycle period of time, you're going to have many, many more rabbits. Take bacteria in a milk jug. When you take it out and set it on the counter, there's only a few bacteria in there because it's been chilled in the fridge. But as it starts to warm and those bacteria grow, when there's only 2 in there, they double into 4. But when there's 400 in there, in that same kind of period, the time it takes for the cells to split, 200 goes to 400. So it's changing faster only because there is more of it. Think about when Adam and Eve were the only 2 people on Earth. In 9 months, the population went up by 1. Now, 9 months, the population could go up by millions, right? So the change in the population is directly related to how big that population actually happens to be. So, even money. If this was interest, so that the rate of change of your money with respect to time is directly related to how much money you have. If you only have $1,000 in the bank, at the end of 1 year, if you make it 5%, you're going to get $50. If you have $100,000 in the bank and you make it 5%, at the end of 1 year, you're going to have $5,000. And so that grew is the same amount of time, but the only thing that changed was you had more of it to begin with. And so that changed the rate at which it grew. And so that is the exponential growth model. And that's where it comes from, truly. This is, again, in the notes. This is just me rederiving it in a different set of notes so you can see where it comes from. But then I want to do a few examples with you in the end. So let's solve dy dx is x times y. Divide by y, multiply by dx. So I got 1 over y dy is x dx. Integrate both sides now that we've separated. See, we have all the y's on one side, all the x's on the other side. So this is separated. Now we integrate both sides. We get the ln absolute value of y. Antiderivative of x is x squared over 2 plus a constant. We e both sides. We get the absolute value of y. Should be e to the x squared times e to the c. E to the c is just another constant, so let's rename it a new c. And the absolute value, why can I drop it? Again, because e to something is positive, and e to something is positive, and a positive times a positive is positive. This side will always be positive, so the absolute value doesn't matter, because population can't be negative. If you had negative people to start with, it would be magic if you started growing a population. So then we say y is c e to the negative x squared. Let's take something like this. Dy dx is x e to the x over y. So on this one now, I'm going to multiply by y to this side, and I'll multiply the dx to this side. So now I've got the integral of y dy is equal to the integral of x e to the x dx. This actually takes integration by parts, but you could do rapid repeated. So if you remember, you put your u here, you're going to use late, and so there is algebra and exponentials. Since algebra comes, the a comes before the e in the spelling of late, the u would be x. We take derivatives until it's 0. We take antiderivatives here, and we go down plus, minus, and so we should get x e to the x minus e to the x plus c. The antiderivative of y is y squared over 2. I can multiply by 2. When I multiply by 2, I distribute, so I got 2x e to the x minus 2 e to the x plus 2c. But 2c is just another c. And so, since it is just another c, I can just suck the 2 into it. And then because it's y squared, maybe we want to solve for y. In this case, you'd have to put a plus or minus in there, and a square root. All right, one more. So let's say 1 minus t dy dt minus y equals 0. So, and then this one, they've given us an initial condition. So right here, they gave us that y of 2 was equal to negative 4. All right, so then to do this, I'm going to add the y over. So there's the y on that side. Divide by the 1 minus t. Now I'm going to divide the y back to the other side. So I've got 1 over y dy dt, but I'm going to multiply the dt over. This gives me 1 over 1 minus t. The antiderivative of 1 over y is ln absolute value y, and the antiderivative of 1 over 1 minus t is ln absolute value 1 minus t, but you need a negative out front, because the derivative of this is 1 over 1 minus t times the derivative of 1 minus t, which is negative 1. And so that negative kills it. So you would need a substitution to have it actually work. To solve, we can e both sides. Remember, the e and the ln have to be right next to each other for the inverse property to wipe them out. And so I had to put the negative up as a power, and I'm using the property of logarithms to do that. That gives me the absolute value of y. I got e to the ln of absolute value 1 minus t to the negative 1 times e to the c. The e to the c, we're going to make a new c again. Then we've got absolute value y is c times absolute value 1 minus t to the negative 1. This is the general solution. And because I don't know if c could be positive or negative this time, notice I haven't dropped the absolute value on here. And it's because I'm not certain this time. Before, I was certain that, in this case, even up here, that can't ever be negative, and that can't ever be negative. And so the absolute value didn't matter. But down here, because I'm not certain, I'm leaving it in there. Remember, this was an initial value problem though, so we have to plug in the initial condition. So that says when x is 2, y is negative 4. So where the y is, I put a negative 4. And where the t is, I put a 2. So then absolute value of negative 4 is 4. 1 minus 2 is negative 1. Absolute value of negative 1 is 1. 1 to the negative 1 is 1. So you get c equals 4. And then now we have a particular solution. The absolute value of y is 4. And I just put the negative 1 power down at the bottom to make it like that. Another cool example, and you probably read about this in the second section I asked you to read, and we actually study it in Math 20, but it's Newton's law of cooling. And Newton's law of cooling states that the rate at which an object cools is proportional to the difference between the temperature of the object and its surrounding environment. What that means is, and think about this, when you take brownies out of the oven and they're scorching hot, after 10 or 20 minutes, they're cooled to where you can eat them already. But after an hour, they're still warm. And after an hour and a half, they're still slightly warm. And so the thing is, as the temperature of the brownies gets closer to the temperature of the surrounding environment, the rate at which it cools slows down. But if the temperature difference is great, like they're 350 degrees and the room is 70 degrees, that 70 degrees is going to cool them off a lot faster than when they're 80 degrees. And so the rate at which an object cools is proportional to the difference between the temperature of the object and the surrounding environment. Let's turn this into a differential equation and solve it. So let's let capital T be the temperature of the object, and let's let little t be the time. And so we actually are looking for a function t of t. That gives us the temperature at any time t. Let's let T naught be the surrounding temperature. And now let's take what Newton said and let's put it exactly to mathematics. So the rate, another word for rate is derivative. So the derivative is proportional. So the derivative is equals. Proportional just means a multiple of. And it said the difference means subtraction, between the temperature of the object, well, T was the temperature of the object, and the surrounding environment, that was T naught. So T minus T naught, that is that difference. Now we separate variables, so I'm going to divide by T minus T naught. So I got 1 over T minus T naught, d big T. I'm going to leave the K over here, and then I'm going to multiply by dt, and I have k dt. You may ask, why didn't you take the k over to this side? Because remember, I'm going to solve for t in the end, and if I move it over here, I'm just going to have to move it back in the end. When I integrate this, I get the ln absolute value of t minus t naught. This gives me kt plus a c. Notice I'm not writing the plus c anymore, the c1 and c2. That we always move over here, and we just have one constant. Now we're going to e both sides. This gives me absolute value of t minus t naught. And this gives me e to the kt times e to the c. But we've said 3 times in this lecture already that e to the c is just another constant. So we get c e to the kt on this side. Now, I really want to drop that absolute value. But I've said, you gotta know if you can. Well, here's the thing. Whatever object you have, if it's warmer than the room that it's in, it can never cool to below that temperature unless it started becoming exothermic and like shedding heat for some reason. And so the temperature of the brownies will always be a little bit warmer or room temperature. And so this will always be a positive value or 0. And since it's always positive because the temperature of the actual object has to be hotter than the temperature of the environment, that difference is always positive, and so I am allowed to drop that absolute value. Then to solve for t, we just add t naught to the other side, and I get t of t is c e to the kt plus t naught. Now, if Ti is the initial temp, so meaning at time 0, the temperature is Ti, let's put that in. So that says little t is 0, big T is Ti. So where big T is, I put Ti, c e to the kt, but T is 0, and then I get plus T naught. Well, e to the 0 is 1, so I just get c, and if I subtract the T naught, I get Ti minus T naught. And the thing is the initial temp minus the surrounding environment is the initial temperature difference. And so C is that initial temperature difference. And if you took Math 20, the formula is actually d naught e to the kt plus ts. And so that's what I was showing you here. That C is always the initial temperature difference. So that does it for those sets of notes. I'm going to upload this video and I will give you a few problems to do. They'll all be on separation of variables. Hopefully with these 2 sets of notes in this video and the book and other YouTube resources, you guys will be successful and be able to accomplish this. Okay? Thank you.